Hello, Physics 30, and welcome to Lesson 35, Nuclear Physics. All right, so what we're going to be doing in this unit, well, the difference between this unit and last unit is before we were talking about, let's say if we had a proton, usually it's hydrogen, right? Because it's the simplest atom. Um, we talked about those different orbital or different electron shells or energy levels that the electron might be in, right? So that was the electron jumping up and then maybe jumping down and emitting a photon, that type of a thing. So now what we're talking about, so that was last unit. Now what we're talking about is if, let's say we take something like helium. So we've got 2 protons and 2 neutrons. Now we're going to be talking about the interactions in here, right? Like in the actual nucleus itself. What's holding these things together, right? So that's the difference. So last unit, mostly electrons and energy levels of like the electrons jumping around. This one is how are things happening in the nucleus. All right. So in order to do this, we need to learn kind of a new language here. Actually, it's just a different way of writing it. You guys have seen a lot of this. You'll know a lot of these things, especially if you've taken chemistry. We're just going to write it a little bit different. So this is called nuclear physics. I know it's kind of, you're going to find that a lot in this unit. Is there was like physicists who were trying to be funny or something. That's you guys will see them when they come up. I'm not sure where they get these names from. All right, so what we're going to do is we're going to talk about some atom. And that atom, could be, just whatever the symbol was. So the symbol for the atom. So maybe that's carbon or something like that, right? And then Z is going to be the atomic number, so the number of protons or the charge, right? And then A is going to be the atomic mass. So the atomic mass there. And when I said charge back there, you guys are probably wondering because, usually atoms are neutrally charged because you've got protons are positive, electrons are negative, and they cancel each other out. But we're kind of talking more so about protons, especially because sometimes we're going to be talking about completely ionized atoms that don't have any electrons. So, all right. So that's that. So if we kind of look at, let's say, tungsten. So quite often you'd see tungsten written in different ways. It would be tungsten, 186. There could be tungsten 185. There could be tungsten 187, something like that. What this refers to is the atomic mass of the element. So that would be written like this, right? So tungsten, you could find on your periodic table, would be W. And then the atomic mass is 186. The atomic numbers, number of protons, is 74. And really what that's saying is that you've got 74 protons. And you could probably figure out then, like everything else in there must be neutrons. So 186 minus 74, there's 112 neutrons. Okay. We're going to talk a bit more about this in a minute, but all of these things in the center of our atom, so protons and neutrons, those also go by another name of nucleons, right? Just things in the center. All right, isotopes. So there is quite a bit in this lesson. So there's some things, so for example, like this stuff here, I'm going to let you guys read. So make sure you do read all the stuff too. Don't just go off of what I'm saying. There's more involved here. But I'm going to kind of skip through a little bit faster. So an isotope in general is gonna be like this, right? So like I've already kind of mentioned that carbon, goes by different forms. There could be carbon 12, carbon 13, carbon 14, right? And what those are really changing is the atomic mass, right? So the number of nucleons. And really what's changing there isn't the number of protons, right? Because the protons are 6 always, because that's what carbon is, right? It has 6 protons. But what's changing here is the number of neutrons that are in that nucleus of the atom, right? So and that's really what isotopes are. They're just different variations of a specific or of a certain atom. Okay. All right, so yeah, this just has you guys kind of write maybe something like this. Oxygen 16 would be written like that, right? Because you got oxygen, there's 8 protons, and there's 16 nucleons. So the atomic mass would be 16, right? And we're just assuming that it's going to be electrically neutral for these, right? It wouldn't be a different isotope of that atom. All right, nuclear equations. So We are going to be talking about conservation of charge and conservation of nucleons. Okay, and what I want you guys to do right now is get your formula sheets and look at the physics data sheet there. What I'm talking about right now on your physics principles here is going to be numbers 7 and 8, right? So conservation of charge and conservation of nucleons. So these are important concepts. They actually come up in the physics principles. So just so you're aware, that is what we're talking about now. So what we're going to be like, it's really not that difficult of a concept here. So if we're writing nuclear equations, then what we do is we split it up between the parent isotopes, or atoms, right? And the daughter isotopes. And it's going to be like two sides of an equation, right? Like the left side of the equation will be the parents, and the right side will be the daughter isotopes. And what I mean by that, maybe it's a bit easier to actually see, like maybe in this example I'll show you in the bottom here. Our parent, if I'm looking at this nuclear reaction, well, this first thing here, that's just one neutron. So I guess that wouldn't really be the parent, that's just one that comes in and causes this reaction. But this isotope is going to be the parent atom, right? So what happens here is this parent atom splits into two different atoms. It will have these daughter isotopes come out of it, right? So it's just left side of the equation equals right side of the equation. It definitely has the form of chemistry, right? You guys have probably seen this with like the arrow if you've taken chemistry classes. So very similar. Now, what's happening here is that we've got, so the sum of the atomic numbers on the parent side equals the sum of the atomic numbers on the daughter side. Well, that actually just makes sense, right? If we're saying the sum of the atomic numbers, remember, that's just the number of protons. So you're saying you've got 5 protons to begin with. Well, there must be 5 protons to end with, right? The sum of the charges all stays the same. And yeah, so that's pretty much all that's going to be happening there, right? And then on the other side of that, so actually just go back a little bit here. So this part here, sum of the atomic numbers on the parent side equals the sum of the atomic numbers on the daughter side. That is going to be our conservation of charge. Okay? And then you could probably guess the next one's going to be conservation of nucleons, which is just the same thing. It's just saying the total number of nucleons, right? So just protons or neutrons before has to equal the total number after. And that's it. There's just, if there's a certain number of protons and neutrons before, there's going to be that same number after, right? So this part here, this is going to be our conservation of nucleons. Okay. And here's just a typical question, and you guys already know the answer because we've been looking at it, but you know, it'll say something like when boron 10, right, so this guy, nucleus captures a neutron, like a rogue neutron, just it gets captured into boron 10, a new element and an alpha particle, so helium, are produced. Write a complete nuclear equation for this interaction. All right, so we just know, okay, well, this neutron plus this boron 10 atom must create helium and then something else, right? Well, we just know that that's something else. My nucleons before, well, they need to add up to my after. So before I had 11, right, on this side, and then after I've got 4, so I'm going to need 7 more. So this must be a 7. Okay, and then same thing on the bottom. So I've got 5 total charge on the bottom, right? Positive 5, because I got 5 protons on the bottom. Well, on the bottom after, I've got 2. Well, this must be a 3. And then from that information, right, from that 3, we can look to our periodic table. So that's why you guys have these, right? You can figure out which one we must be talking about. So if I go back here, it's the atomic number of 3. We must be talking about lithium, right? Lithium. Okay, so that's where that comes from. All right, probably been talking too long about that one. All right, moving on. So atomic mass units. So atomic mass units were created for really the same reason. You know, in the last unit, how we, instead of talking about things in like, you know, like a really, really small number of joules, we created electron volts, just to use more kind of nice numbers. Well, we're going to do the same thing now with atomic mass units. So instead of talking about things like, very, very small, and we can't just write it this way anymore as 1.67 times 10 to the negative 27 for the mass of, let's say, a proton or a neutron. I'll just remind you guys on your formula sheet here. The mass of a proton and electron, or proton and neutron, right? They're both right here. That's all you have on your formula sheet. Well, for this unit, we're going to have to be more accurate than that. We're actually going to be using numbers like this, right? So here's our mass of a proton, and here's our mass of a neutron. Turns out they are slightly different if you go to more decimal places. So then instead of us writing these things down, what we're going to do is we're going to replace that with this 1.001 or 0.007276, right? Instead of the times 10 to the negative 27 part of that, right? And this is going to be called an atomic mass unit. Okay? And just so that you guys aren't scared right off the bat, because you're like, well, where is this? I don't have this on my formula sheet. You'll be given these numbers in a question if you need it, right? So if there's a specific question, you'd be given that, right? You don't have to memorize those numbers or that many digits or something like that. Okay, so what they did though to figure out this atomic mass unit is they took the mass of a carbon-12 nucleus and then they divided it by 12, right, to figure out how much each individual proton actually weighed there, right? So that's how they define the atomic mass unit. Okay, well, so where 1, would be like 1 proton, right? Atomic mass unit of 1. So yeah, 12 divided by 12 is really 1, right? But then you might say, well, that's not what these equal. Well, that's because they came up with these numbers later. They got more and more accurate and figured out that they were actually, not accurate enough when they did it the first time, right? Okay, so that's what they did. And then again, you might also have the question and say, well, okay, why would they take carbon-12, right? That just had 12 things, right? Pretend those are all nucleons, right? Why would they take those 12, and then just divide by 12 to figure out what the mass of one of them was? Like, why wouldn't they just take the mass of one of them? Take the mass of a hydrogen atom, right? Why would you need to take carbon and divide it by 12? Well, that actually gets into the next part of this. The reason why you can't just figure out what the mass of one proton is, well, you can, but what's going to happen is they'll be different. And that comes to our next part here. It's called the mass defect and the mass energy equivalence. All right, so what this means is, well, what happened was scientists discovered that the nucleus contained protons and neutrons, right? So they were figuring this part of the puzzle out. They were able to calculate the theoretical mass of a particular isotope by adding together the masses of the protons and neutrons, right? So they know the mass of like a proton and the mass of a neutron. So they're like, okay, well, protons plus neutrons equals just the mass of our atom, right? And then you might be saying, well, what about the electrons, right? Well, electrons are just so small, they just don't really come into play here, right? The mass of the proton and the neutron are just way more, so we don't even worry about the mass of the electron. Pretend they're not even there. All right, so then what they did is they say, okay, well, we know what the theoretical mass should be just by adding them together, okay? Then what they did is they used a mass spectrometer. So the things we've done in other lessons, right? We've done a lot with mass spectrometers. Then scientists were able to find the measured mass. They were expecting the values to be identical, right? So, okay, so we actually send this thing into a velocity selector and then send it into a magnetic field and then figure out from, the curvature what the actual mass was. But it was different was the thing, right? So what happened here is that they figured out, well, okay, the theoretical would be 2 times how much we know a proton is, and then 2 times how much we know a neutron is. So it should be this number of atomic mass units, yeah? But then we do a mass spectrometer and then figure out that it's actually only this much, right? It's like it weighs less than those 4 things do to, like, just adding them all together, right? Just take a second to think about it. Just that is strange. That's a really strange idea there, that you can take 1, 2, 3, 4 of something, right? Figure out what the mass of each 4 of those are, and then you put them all together, right? That's all it is those four. Put them all together, right? So they're closer, just one atom. And this one weighs less than that one. That's weird, right? That's weird, and everybody knew how weird that was when they found it. So what they did, though, or what I should say, what was Einstein measured the difference between them, right? And then used his probably the most famous equation of all time. You've probably heard of that one. E is equal to mc squared. This is the mass energy equivalence, right? And what this equation is saying, if we just take a minute here, is that energy, right, that's what the E stands for, is equal to mass and then times the speed of light squared. And what this means is, it's really strange. This is saying that energy is pretty much the same thing as mass, other than it's being multiplied by the speed of light squared. Right? So mass and energy are actually like just two sides of the same coin. They're the same thing, really. And the other crazy part of this is, if you think about it, you've got energy is equal to, and well, let's just throw a number in here. Let's say 1 kilogram. Okay, 1 kilogram of something, right? So not very much, times, and then the speed of light squared. So you guys know that. That's 3 times 10 to the 8 meters per second. And then that squared, right? That is a gigantic number. So you're going to have that much energy just from one. It's worth probably writing down. This would be an energy of 9. That many joules of energy. That is ridiculous, right? Like, you get like a crazy, crazy amount of energy out of a very, very small amount of mass, right? So it doesn't take much mass to make a huge amount of energy. All right, so just I got off track there a little bit, but going back to this mass defect, right? That's what this is. Change in mass is our mass defect. The difference between what we actually measure and what we actually predicted the theoretical was, that's going to be really what's missing as energy. So the missing mass, right? So when I was talking about this up here, right? It's like these ones didn't weigh the same as these ones. Well, the difference between them is actually in the form of energy, and that's why the missing mass is in the form of energy. Okay, moving on. Okay, so just a quick little question here. I kind of did the same thing, right? If you take just like even like this huge amount of energy and convert it to mass, well, that's only this tiny, tiny little bit of mass. So just using our equation. Okay, so then what happened there was a new term here. It's called binding energy. So what that is we're saying it's the energy. So again, they use helium a lot, right? So if we've got 2 protons and 2 neutrons, so what's happening here is it actually requires, because remember, these protons don't like each other. They are constantly trying to repel. They're both positive, right? And they're really, really close. They're trying to repel a lot. There's a big force happening there, just a big FE force, electrostatic force, right? So something is holding them together, right? And what that something is, it turns out, is called the strong nuclear force. And we're going to talk about that later, but it's a brand new force, right? So far we've talked about the force of gravity, and we've talked about the electrostatic force. And that's pretty much it, right? We haven't really talked about any other forces like ever. Well, you guys might be thinking, well, what about the force when you actually push something, right? If I push a block. But if I that actually, in the end, we're going to talk about this too in another unit, that really is just an electrostatic force. Yeah, getting ahead of myself though. Anyway, so we're bringing up a brand new force that you guys probably haven't heard of yet. And this is the force that's required to hold these guys together. It holds the nucleus together. Well, that force that's holding those together, right? That binding energy, or the force like that's holding everything in here all together, that is what, so that's energy, right? But energy is equal to mc squared. So that's what our missing mass was. It's the energy holding those guys together. And then what can happen, right? If we pull those things apart, or actually I shouldn't say in this case, if you had a really, really big atom and you pulled those things apart, right? Well, now you've released a bunch of energy. All that energy that was holding that together in the form of mass gets released, and now that just gets released as energy. Well, that's what a nuclear reactor is, and that's what like a nuclear bomb is, essentially. Okay, we'll talk more about that, though, too. All right, so you guys can look through this one to figure out the binding energy. One thing I think you guys will be fine with it, right? Figure out the theoretical is going to just be adding up all your protons, all of your neutrons to figure out the total energy. And then what you would do is figure out your mass defect. So just subtract what the energy was found, or sorry, what the mass was actually like measured to be, right? In a lab using a mass spectrometer, was measured to be that. And then subtract what you thought it should be, right? The theoretical, right? So then notice here that we end up with a negative number. You should get a negative number for your mass defect. It's like the energy that's kind of missing, right? It's the energy that's going into holding the atom together. Then though, when we convert this into energy, this formula, this E is equal to mc squared, only works with a mass in kilograms. We have to change it back from atomic mass units back into kilograms. Okay, so on your formula sheet, you guys can see this, and that's right here, right? One atomic mass unit is equal to 1.66 times 10 to the negative 27. So, oh, that's wrong. So 1.66, right? This one has more digits. So again, if you were given, like, this would be in a question, right? They would tell, like, if they wanted you to be this accurate, that would be in the question. If it wasn't, then you could use the one on your sorry, I think I just paused it. Then you could use the one on your formula sheet of just 1.66, right? But you just use the more accurate one if you're given that. Okay, and then you end up with a certain number of joules. So not a huge number of joules, right? But this is for every atom that's happening. You're getting this much. So it would add up to be a huge amount of energy in the end if you had like a nuclear bomb or something going off. Okay. Conservation of mass energy. All right, so I'm going to go through this a little bit quick because I kind of was already talking about this in general. So conservation of mass energy is the idea allows us to imagine the creation of particles from kinetic or radiant energy and to imagine the annihilation of particles. So what this really means, so what we could do is actually just imagine mass, so here I'll do it the other way, energy and mass as being the same thing, right? Because remember, they're just a c squared away, right? That's the only difference between them. So if we took, let's say, an electron, if you have the mass of an electron, well, that could just be considered the energy, right? If we just put this mass in, just insert mass, and then multiply by the speed of light, this is like a really accurate version of it, we just end up with, well, this many mega electron volts, right? So just the unit of energy, like we've done in the last unit there. And then on your physics data sheet, I just want you guys to know this too, that coming up here, like in lesson 37, we're going to start talking about, let's say, like the mass of an electron, like in a slightly different way. You'll see that it's written like this, where we've got the mass of an electron is actually 0.510999 mega electron volts divided by c squared. And it's a mass, right? Like, so these units here are just a different way. It's just a different way of saying, well, not a different way of saying kilograms, but it's equivalent to mass, right? So instead of kilograms, we've just got a new unit that's in energy over c squared. And it's all just from this equation. It's just rearranging to get this, right? Okay. And just so you can see what I'm talking about, it's right here, right? So mass could be written that way, mega electron volts per c squared, or speed of light squared. All right, nuclear reactions. So why nuclear reactions are so energetic is we can get like a bit of an idea here. If we think about, well, in the last unit, right, we talked about ionizing an electron, right? So it takes 13.6 electron volts for hydrogen to completely ionize it, so completely give that atom enough energy to strip the electron away. But it would take 8 mega electron volts of energy to remove a nucleon from the nucleus. So a lot more energy bound up holding the nucleus together than there is holding the electrons together, right? And this is really talking about the difference between like chemistry or chemical reactions and nuclear reactions. Chemical reactions are releasing the energy that's used to hold atoms together, because the same thing actually happens with the, E is equal to mc squared. This same thing happens where some energy is wrapped up into like holding two atoms together in a molecule, right? For like a chemical reaction. And when you break those bonds, you release energy. And that's enough energy to give us like, fire and other sorts of chemical reactions that, seem quite explosive. Well, even like jet fuel, right? Jet fuel itself is just really converting the energy that's holding these atoms together and breaking those bonds and releasing it in the form of energy. So it can be quite a lot. But when you talk about nuclear reactions, it's like a whole nother level, right? Like nuclear reactions are gonna produce way more energy. And that's how we end up with the energy, like such an intense amount of energy to actually fuel our sun, right? That's how stars work, is through nuclear reactions. And then we've actually made nuclear reactors, right? That can turn mass, like they actually split apart big atoms and turn that into energy. But you get way more bang for your buck in nuclear reactions. Okay, so yeah, that's pretty much it. Different types of reactions. So we've got induced nuclear reactions. So what can happen is that we have an atom sitting here, right? We've got just some kind of atom. And then you've got usually like a neutron, or like a gamma ray, something that has some energy. And then what that does is that like gives this guy enough energy for a second that it breaks up into two other daughter nuclei. So those are induced nuclear reactions. It's like it didn't have enough energy to like break apart into its two daughter nuclei until we presented it with more energy by introducing a neutron or an electron or a gamma ray or some kind of energy, right? So that's why it's induced, right? And that's where the induced part of that comes in. Okay. So here's like a typical example. You've got nitrogen sitting there, and then it's struck by a helium nucleus, so alpha particle, and then it would split up into actually, I'm sorry, in this case it's not that it splits up, it actually just creates. So this one just smashes into this one and creates this, but it wouldn't always happen that way. Sometimes it would break into smaller ones as well. All right. So here's an example of that, right? You guys don't need to have all of this memorized on like how this type of a thing could happen. But here's the idea, is that maybe you start out with uranium-238, and then it's struck by a neutron, like a rogue neutron. And then what that's going to do, since I've, conservation of nucleons, that's going to create the same number of nucleons to have uranium-239. But then uranium-239 doesn't like sitting there with that extra neutron on there. So within like, milliseconds, this thing will instantly create a gamma, instantly this thing will decay into neptunium, into something else, right? And then that neptunium would also release an electron, right? So an electron has 0 nucleons, but it has a charge of -1. We haven't talked much about that yet, but we will. And then this symbol here is a gamma ray. So that's just radiation. That's like just the leftover energy. Okay, and then Neptunium-239, again, it didn't even like sitting there, right? That was unstable as well. It decays into plutonium-239 plus an electron plus a gamma ray, right? So this whole reaction all started to take place just because we hit it with a neutron. Okay, so that's the idea there, that it can be induced, this whole process. Like I said, you won't have to like know exactly what happens, right? That's actually quite difficult to figure out exactly what would happen there. Okay. All right, so fission reactions. So with a fission reaction, it's a type of nuclear reaction. What they do is they take heavier atoms. They'll strike it with a neutron, and then that will split into two different daughter nuclei. So it kind of looks like this, right? Here's our incoming neutron. It hits this big atom, and then what will happen is that will cause this thing to split into two parts. And just one misconception that always happens here is people think that this thing has enough energy that it just like smashes into this and blows this thing apart. That's not really what happened there. What happened there is you gave this uranium atom enough energy that it was unstable, and then it was more stable when it was in these two separate pieces. So that's the way it went. It's not that it blew it up into two pieces. Okay, so it blew them up into, so it didn't blow them up into two pieces. It just became unstable and then separated into two pieces because that was a lower energy state. But then some other things can happen. So it split into these things plus 3 extra neutrons and then energy. And this energy is what we wanted, right? So when we make nuclear fission reactions, like in nuclear power plants, right? We want the energy out of it. We want it as really heat. We turn it into heat, and then that heat we can turn into like electricity or, well, yeah, usually electricity when we do this. Yeah. So that's pretty much it with nuclear fission. And then what's going to happen there, though? So this was one reaction, but notice after this reaction took place that we created 3 extra neutrons. Well, remember, it was a neutron that kind of started this whole thing, right? Like a flying, like a rogue neutron that hit our uranium atom to begin with. So imagine now we've got these extra neutrons flying around. Well, they are going to go and find their own uranium atoms to interact with and then make this whole process happen again. And you can see like what would happen, right? You got neutron comes in, creates this nuclear reaction, and then you've got 1, 2, 3 more, and then those create their own reaction. This is an exponential growth, right? This thing is going to get really big really fast, and that really is a nuclear bomb, right? If you let this go out of control, then that's what like the bombs that were dropped on Japan really were, right? There was just this reaction getting crazy out of control. And I shouldn't say that that was what caused. There was a little bit more to that with a nuclear. Like there's like something called like a hydrogen bomb, and what they do there is they kind of use both. They use a nuclear fission reaction, so this process of like crazy out of control reactions, but then that will actually cause a nuclear fusion reaction, and I'll talk about that in a second. That's the next part here is nuclear fusion reactions. So, yeah. Okay, so you guys will need to know just some of the pros and cons of fission reactions and fusion reactions here in a second. But fission, so what we're doing now, fission is the breaking up of big molecules, or atoms, I mean, sorry, not molecules, big atoms, into smaller ones and releasing the energy in between. And the main problems are that uranium-235 is very rare, right? You have to mine for it, which takes a lot of energy, and it's hard to get to produce these. That being said, they do have other sorts of atoms that are good contenders, and they're getting better at like making reactors out of different types of isotopes all the time. So that's one that I think there's a lot of progress with in finding different fissionable materials. The process, so number 2, the process produces large amounts of deadly radioactive waste that must be carefully stored. If you think about, that's always the big one, right? When people have a problem with fission reactors or nuclear reactors, it's always that. Like, what do you do with all the waste, right? Well, I don't know. I'm kind of biased on this one. I think you can bury it. Like, I think that we have lots of ways to deal with radioactive waste. Even with solar cells, right? There's batteries. We have to deal with all the waste from the batteries when we're done too, right? So I think like the amount of waste that's actually produced is actually quite small. It's something that we could handle just based on documentaries and things I've watched too. So Anyway, though, that's very political question. Number three says the reactors are subject to human and mechanical failures, which can be catastrophic. So Chernobyl, right? You've got Chernobyl, you've got the Fukushima in Japan there with the, I don't know if you guys remember that, with the tsunami that hit, and then the reactors went into a meltdown. Yeah, so that is true. Like we can definitely have meltdowns, and we have to think about things like Chernobyl. But again, from like I really think this is like we shouldn't base the problems of today and like what we can do today on the technologies of yesterday. Chernobyl was they were terrible nuclear reactors. That if you had our Canadian reactors, they wouldn't do what Chernobyl did. They can't melt down in the same way. They have like way more safeguards and like they really are very safe. Same with Fukushima. The Fukushima plant was a very unsafe reactor. It was like a really old reactor, and it should never have been anywhere close to a fault line, right? So again, I don't know. Like I think if we're actually gonna combat climate change, I think people should be a lot more open to nuclear fusion in the future. That being said, we also have I forget what percentage it is, but in France, most of their energy comes from nuclear fusion, and they're doing really well. So okay, again, I'm probably a little biased on that, but I don't care. All right, so this really will just be the process of nuclear fission reactions. It's figuring out the mass defect, right? Because that mass defect, that is, if I change that into energy, that's how much energy is going to be released, right? So same type of question as we did above. All right, fusion reactions. All right, not to be confused with fission reactions. Fusion versus fission. I know they couldn't have made closer names, right? But fusion reactions are what fuse smaller atoms together. So let's say we've got two protons, right? So helium, or sorry, two hydrogen atoms, and then we can fuse those guys together. Well, that's gonna, and then in the end, add a couple more neutrons. We've now got hydrogen, right? Or helium. Sorry, I'm mixing those up. And we've now got helium. So what'll happen here is you've got, well, my little picture there is pretty simplistic. That it actually happens in a few steps. But if you take something like deuterium, so that's this, right? So you've got hydrogen with, so it's one proton, but it has another neutron, right? So this would be a proton and a neutron together. And then you bring two of those together. You end up getting not quite like a stable helium, not helium-4 yet, but you get helium-3 plus another neutron. And then you get heat out of that. Because these two guys to begin with have more mass than those two do, right? So the missing mass that was left over was the heat, right? You might be a little bit confused by that in a second because I've been talking about like going the other way, right? Like how with nuclear fission, how did we get energy out of it then if the two to begin with had more of a mass than the two at the end, right? It was kind of the opposite before, right? But I'm going to show you like a picture that's going to kind of explain that, I think, here. But so here, the problem with this of like bringing these two together, though, this is really it. How do you? Oh, sorry, I forgot the next step here. The next step is you would have hydrogen. Sorry, this is actually just another way it could happen. So you've got hydrogen 3, or a tritium, and then a deuterium, so hydrogen 2, and then that can create a stable helium. So there's actually a few things that can happen there, and I got a picture of that down below too, but that's not the main, like the main focus is just that you take two things, you smash them together, you bring them really close together, and then they form into a brand new atom and heat. This is what's powering our sun, this heat right here. This can be like changing this small amount of mass into energy can have a really big effect, right? So I'm talking a bit about this. Yeah, so and the only place that this can happen, is in places of extreme pressure. So what's happening at our sun, at the center of our sun? Well, I don't know if you guys know this, the sun is really massive. It has a lot of gravity pushing in, right? All of that gravity pushing in forces all of this stuff in the center to be under incredible pressure. So that incredible pressure forces all the tiny, tiny little hydrogen atoms all together, which forms helium, right? And then from that helium, if the star is big enough, in an area outside of that, let's say all of this was helium outside here, well, now that's the right pressure there to convert all of that helium into lithium, right? And then that'll create that, and that'll keep on going up and up and up. Turns out all of the stuff in our universe, all of the matter that we know of, happens at the heart of a star. Actually, I shouldn't say it happens at the heart of a star. A lot of the elements, all of the lighter ones, right? So here, I'm going to bring up our periodic table here. All of our lighter ones, so we've got hydrogen, oh, no, I can't write on this, sorry. We've got hydrogen, helium, lithium, beryllium, boron, and carbon, all the way up to these ones. Most of these ones, actually all the way up to iron, all get formed in the heart of a star. But then the rest of them, what happens is that, you guys have probably heard me talk about this in class, it's called a supernova. So eventually, when all of our fuel runs out at the center of our star, well, when that fuel was running, we had pressure pushing out because of the heat it was creating, right? So this thing was stable. The pressure in was equal to the pressure out. So now we've got a stable star. But now you run out of fuel, and we've got all that pressure pushing in. This is what a supernova is. It's the collapse of a star. So all of this mass, remember this thing is huge, goes rushing in like close to the speed of light, hits the center, and then bounces back out again. All the stuff bounces everywhere outside the star. Well, all that stuff traveling in and all that stuff traveling out smash into each other at incredible speeds. And this is where we get the rest of our atoms from. So everything past iron, like everything else on the periodic table, all comes from exploding stars. But in the end, everything around us is all from a star. Except for hydrogen. And some helium, I guess. So those things started at the Big Bang. But everything else. All right. Okay, anyway, that was a bit of a tangent. All right, so the materials required to produce fusion reactions can be found in anything, right? So in a pail of water. So we've got, if you just took 4 cents of water, that actually has the potential to match 300 gallons of oil for the amount of energy that it produces. Okay. Yeah, the problem is that we don't really have any great way of creating it. We can, though. I shouldn't say that. We actually do create. I say we like I did this. They can force 2 hydrogen atoms together, right, or 2 protons together to create fusion. But the amount of energy required to do it isn't worth the energy you get out. I think they have it now, so you get like slightly more energy out than what you put in, but it's not efficient, right? We can't really do this in a great way right now, but they're working on it. There are some there's some hope that we will have like nuclear fusion reactions in the future, and they'd be super safe. There'd be like there's no byproduct. Like the byproduct is just like a little bit of water in the end, right? There's like nothing to it. And the way they're doing it is actually, like the one I was watching, is they actually have like, I think it was 10 of the world's most powerful lasers all focused on like a tiny, tiny little area. They just focus it in, and that has enough energy to actually turn those 2 protons or smash them together, right? But it takes a lot of energy. Okay. So element formation. So this is actually just another picture of kind of what actually happens to turn hydrogen atoms, so these protons, into helium atoms. So this is, you'd have a reaction like this one, right? 2 hydrogens turn into hydrogen 2, right? And it's happening again. It's happening over there as well. And then in comes maybe a third one to create hydrogen 3, and then these 2 hydrogen 3s smash into each other and create a stable helium 4 nucleus, and then 2 more protons that would carry on looking for something else to smash into and create another reaction. But yeah, but it takes a lot to bring these guys together. Oh, yeah, we're going to talk about why these two protons might have turned into, let's say, a proton and a neutron. It has to do with this positron, which you haven't heard of, being created, but we're going to talk about that later. All right, here's a good little picture too of the differences between fusion and fission. So fusion is happening on this end, right? So it's happening over here. So imagine we've got, hydrogen, and it has binding energy per nucleon on this side, right? So the amount of energy required to push them together in this case, right? And it turns it into helium. The helium's over there. Well, the amount of energy in between here, that's the amount of energy that's being released when this happens. So if I smash hydrogen into helium, it creates all of this energy, okay? And then when helium turns into, let's say, lithium or carbon, it'll release less, but still quite a lot. And then all the way up, and you can see all the way up to here, all the way up to, and it turns out to be iron. Once it gets up to iron, there's no energy liberated from it anymore. It actually, there's nowhere for it to go. So remember, I said with a star, right, is you had, this first shell would be hydrogen into helium, and then, helium into lithium, and it goes up and up and up, all the way until the point that we end up getting iron. Well, that's it. There's nowhere else for it to go. It's like it's not creating any more energy going out, right? There's no more new reactions happening after all the fuel runs out. So as soon as you start making iron, then that's it. That's the death of the star as soon as iron comes around. So as soon as iron comes around, then it's going to be the pressure on the outside of the star pushing in that wins and collapses this thing down, because it can't create any more nuclear reactions anywhere else. The other thing that's kind of neat that happens is that so you've got these circles, right? Once the hydrogen runs out, well, now you've got helium, right? But helium's not as energetic as the hydrogen reaction. So what ends up happening is the star ends up swelling up really big in order to like have a bigger, like more reactions happening in that bigger space, right? So it ends up swelling up really big, and then you run out of like helium, let's say, and then the star swells up even bigger until it actually gets so big that they say when our star dies eventually, it's not going to go supernova, but before it eventually dies, our star will actually probably engulf the Earth. It'll be that big. It swells up to be a supergiant, it's called. Yeah. So anyway, once a star creates iron, it explodes, right? It goes supernova. And then once it goes supernova, it creates, like I said, all the different atoms in the universe. But then what's happening on the other side here with fission is that if we go over here farther, right? So these other atoms that we have, like plutonium, well, if we split that apart and create some other atom, let's say farther down the line here, well, these other atoms farther down the line have energy, right? So it's this energy here that's we're releasing when we do fusion. It's the difference between the binding energy, right? And it's all kind of based on this chart. So you can get energy from smashing them together from when you go small atoms to big atoms, and you can get energy when you go big atoms and then break them into smaller atoms. Yeah. Okay, hopefully that made sense. All right, so beyond iron, yeah, so that's what I was talking about, yeah. Okay, so just for the sake of time on this video, so I think what I'm going to do is actually I'll write the questions down, or the answers down, and then, I'll have you guys try them and then just like check your work with my work when you're done. So you guys can pause it now and then just push play in a second and I'll have all the answers just pop up at you. All right, so try them now. Okay, so let's explain these now. A lot of you guys just waited for me to do this, didn't you? Okay. All right, so here's what we got. So the first one here, right? So proton enters. Remember, proton is just hydrogen, so that'd be H, and then 1, 1. So yeah, and then beryllium 9. So beryllium is 4 on the periodic table, but then 9 is the atomic mass. And then helium looks like that. And then left over here, right? You've just got your conservation of nucleons, right? So you've got 10 before. Well, we got to have 10 after. So this must have been a 6. And then on the bottom, I've got 5 before. I got to have 5 after. So that must be a 3. And then what I did is I looked at my periodic table and I looked for 3. Right, and 3 ended up being lithium, and then I knew it was lithium 6. Okay, next one. What is the binding energy in one atom of strontium 86? And they give you the atomic mass, or sorry, the mass in atomic mass units. What is the binding energy per nucleon? All right, so what we had to do first was just figure out the binding energy of the whole thing. And then really per nucleon, I'll cut to the gist here. We just had to divide by the number of nucleons. But all right, so the theoretical mass is what we're going to find first. So you're going to go theoretically, this thing should have this mass. It should be 38 protons. So I'll go by the mass of the protons. And remember, like I know I feel a little bad actually because you guys don't have this number on your formula sheet, right? And I just kind of plucked it out of thin air. I'm getting that number from above, right? We had a table that actually showed these. Like I said, if you guys were doing a question like on a diploma or something, they would give you that number if that was the number you were supposed to use. So sorry if your numbers are way off because you're not as accurate as me. Yeah, sorry. Anyway, so that's the number you'd use for protons, and then for neutrons, you've got that one. So 48, so you've got 48 neutrons. So in the end, theoretically, this thing should have a mass of that. Then the mass defect, right, my change in mass, would be, well, what the mass actually is minus my theoretical, right? So what it actually is minus my theoretical. So I end up with a difference of negative that, right? So I was missing that much. Then the next step down here, I converted that atomic mass units into kilograms. And again, this number isn't this accurate on your formula sheet. So if they wanted you to be, they give you that really accurate one. Yeah. So multiply by that, we end up with negative 1.3, yada, 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 times 10 to the negative 27. And notice I'm keeping lots and lots of digits because it really does matter down to these little digits in these questions here. So, okay, so we got that many kilograms. All right, so now that I have it in kilograms, now I can use my, well, I never wrote it there, but that's E is equal to mc squared. Oh, E is equal to mc squared part, right? That's what this line is about here. So that's the mass times the speed of light squared. So I get this many joules. And then finally, just to match my units or my answer with this answer, I can divide by 1.6 times 10 to the negative 19 joules to get it in electron volts, and then write it as mega electron volts. So this is the binding energy for the whole atom, right? And then the second part just says, what is the binding energy per nucleon? Okay, so this is the binding energy for all 86 of these things. I'm just going to divide by 86 to figure out how much it is per one, right? And then that's the same number that we get up here. Okay. Next one. This one's not so bad. So calculate the amount of energy released per atom when radium-226 undergoes alpha decay. So yeah, I kind of thought about it after. I never actually went through one of these, like just through the example part of it. So hopefully you guys maybe figured it out. But it's really going to be your mass defect is going to be, well, it kind of makes sense, right? That the difference in the mass of these guys, right? The difference of the mass after to the mass before must be the missing mass, right? Like if I just weighed all of this stuff before and then weighed all of the stuff after, that's got to be my missing mass that turned into energy, right? So that's all this says down here. It's the mass defect is equal to the sum of the mass of the product, so adding them all together, minus the sum of the mass of the reactants. Okay, so that's all I did. I just added up my products first, right? So the things after, those are my products. And then minus my reactants. And then we got, this number here. And then in atomic mass units, right? Because that's what they gave us. And then I converted that by multiplying by yada, yada, yada in kilograms per mass unit. And then got my answer in kilograms. And then from there, used E is equal to mc squared to just get my answer in joules. And my answer here was in joules, so that was good enough. I could have also changed that into electron volts if I wanted to, right? All right, so hopefully you guys were okay with that. I know that was a long one. I feel kind of bad. We're pushing an hour here, and it probably took longer because you actually had to do these questions. So, yeah, hopefully you guys are understanding. If you need to, email me, and I'll help you out. All right, talk to you later.